Hello and welcome to another installment of Dave Does Calculus at Home. Today we're gonna finish section 9.3. Section 9.3 talks about differential equations. This is going to be video number 3 about differential equations. First two were a little rambly. Sorry about that. It happens. This one hopefully will be a little more focused. There's some very specific things that I want to talk about. Two things in particular that we didn't cover thoroughly, or I guess at all, in the other videos. We need to pick up in this video. We're going to talk about particular solutions, and we're going to talk about verifying solutions. And I'm just going to get right into it with an example. The first example I want to do today is going to look like y prime equals 4t square root of y. This is an equation. It's got an equal sign in it. It is a differential equation. It involves an unknown function, y, and derivatives of that function, y prime. Looks like the independent variable here is t. So when I do step 1 and swap out a y prime for Leibniz notation, I'm going to call this a dy dt instead of a dy dx, so that it matches this variable here. And these things don't change. Now we need to separate this stuff, assuming that it is in fact separable. It looks like it's separable. It looks like everything here is multiplication and division. It usually means you can use multiplication and division to separate this. I'm going to put all my t's on this side and all my y's on this side. So that's going to involve dividing by the square root of y and multiplying by dt. And then I'm going to do one more step here because having a square root in a denominator seems like a pain. I'm just going to rewrite this as y to the negative 1/2 dy equals 4t dt. So this is me starting with a differential equation, switching to Leibniz notation, and then separating it. On the left I have nothing but y's and dy's. On the right I have nothing but t's and dt's. This is now completely fully separated, and I can move on to the next step, which is take the integral of both sides. The integral of y to the negative 1/2. I'll come up here for this. The integral of y to the negative 1/2 is y to the positive 1/2 divided by 1/2, but dividing by 1/2 is the same as multiplying by 2. The integral of 4t dt is going to be 2t squared. I only need one c. I'm going to call it c1 because it's probably going to change. This is an implicit general solution. It is implicit because it is not yet solved for y. It is general because it involves an arbitrary constant here, which could be anything. This doesn't really represent a function. This represents an infinite family of functions. If you pick a number for c, if c is 0, then this is one function. If c is 1, then it's another function. If c is 2, then it's a different function. But they all have the same properties. All of this infinite family of solutions solve this differential equation. So we are going to move to turn this thing into a explicit solution. We can divide everything by 2. That would give me y to the 1/2. So this is the square root of y equals t squared plus. When you divide everything by 2, Dividing this by 2 is pretty straightforward. That'll just give you t squared. Dividing this by 2, if this starts as an arbitrary constant, dividing it by 2 just gives you a different arbitrary constant. So I'm not going to write c1 over 2. I'm far too lazy for that. I'm just going to keep calling it c. I will change the index to indicate that it's a slightly different c than what I started with, but still just an arbitrary constant. And then to get this explicit, I will square both sides and say that y equals t squared plus c2 quantity squared. So this is now an explicit general solution. And again, the general solution means that it contains an arbitrary constant, which means that it is an infinite family of functions, depending on what c is. And so far, this has been a review of what happened in the previous videos. We took differential equations, we separated them, we found explicit general solutions for those differential equations. In today's video, I want to go one step further than that so that I can talk about particular solutions. Particular solutions are what you get when, instead of leaving this as an arbitrary constant, we use some initial values to figure out exactly what this constant needs to be. This is a good problem to sort of illustrate this with because we can visualize something like this with some sort of relative ease, I think, as soon as I find my eraser. Okay, I'm going to erase the left half of this so that I can draw some pictures. Depending on what c is, this function is going to sort of just be in different places. For example, if c is 0, if c2 is 0, this function looks like y equals x to the 4th, which kind of looks like this. Or t to the 4th, I should say. This is the solution you get if c2 turns out to be 0. If c2 turns out to be 1, then we get t to the 4th plus 2t squared plus 1. So probably get something that's a little higher, maybe a little more skewed that way. If c2 turns out to be 2, we'll get something that's even higher, maybe this direction. If c2 is negative, then we'll maybe get something over here. So depending on what c2 is, you'll end up with one of these quartic-looking parabola-ish shapes. So the question then becomes, how can we figure out exactly what c2 is? And the way that we're going to do this is we're going to look at an initial condition. And the initial conditions are going to be given to us as part of the problem, and they're going to look like points. So when you get this problem, it'll include an extra line. It'll say something like y of 1 equals 4. And this means that when t is 1, y is 4. This is basically just like the point 1, 4. Which tells us that from among this infinite family of solutions that all kind of look like this, we're looking for the one in specific that goes through the point 1, 4. Presumably only one of these infinitely many curves will pass through this point. and we can use it to find out what c has to be. And then that will be the particular solution for this differential equation with this initial condition. So I'm going to erase the drawings of this function. Actually, finding C2 is pretty straightforward once you have a general solution. You basically just take these numbers and you plug them into your general solution. So if y, this initial condition tells me that y is going to be 4 when t is 1. Now I have an equation of one variable that I can solve. So the numbers that you can square to get 4 probably going to be 2. So 2 equals 1 plus C2. So C2 probably equals 1. So the particular solution, this is the general solution. The particular solution is going to look like just like the general solution, where y and t are variables, except C2 is going to be a number this time. So the general solution has an arbitrary constant. That's what comes from just the differential equation. Once you have a general solution, if you have an initial condition, you can plug that in, solve for the arbitrary constant, and then rewrite your general solution with a number instead of that constant. And then you have a particular solution. So that's all you have to do for that. The other thing I want to talk about today is verifying a solution. So a lot of steps went into us starting with this and ending with this. And there's a lot of potential for things to go wrong, for us to make a mistake, for something to go sideways and us to end up with an answer that doesn't make any sense. So these are the kinds of problems where it's usually a good idea to check your answer. And checking our answer in this case should be fairly straightforward. Y ought to be t squared plus 1 quantity squared. We can use that to find y prime and check to make sure that it equals this. If y is t squared plus 1 quantity squared, then y prime should be 2 blob to the 1 times the derivative of the inside, which is 2t. And this is going to be t squared plus 1. So I can use the chain rule to find the derivative of y. If I simplify this a little bit, it's going to look like 4t times t squared plus 1. And now we can compare. Does this 4t times t squared plus 1, this is y prime, does it match what I get if I take the square root of y and multiply that by 4t? The square root of y should be t squared plus 1. If y is t squared plus 1 quantity squared, square root should just be t squared plus 1. So 4t square root y should be 4t times t squared plus 1, which is exactly what we get here. Y prime is 4t times t squared plus 1. 4t times the square root of y is 4t times t squared plus 1. These things match. This is how you verify your answer. On the one hand, you take a derivative. On the other hand, you do these operations. You see if you get the same result either way. And in this case, we do. So this has been my example for solving an equation, getting a particular solution, and verifying our answer. Looks like I just hit the 16-minute mark on this video, so I'm going to do another example. In the interest of having that example not being automatically cut off by this camera's stupid video length program, I'm going to cut the video here and do a second example in a fourth differential equations video.